Okay, hello everyone. Welcome to the MIF++ seminar. So today, Professor Alexey Garber will talk about lattices, Parallelohedra, and the Voronoi conjecture. Over to you, Alexey, please.
Yes, thank you, Vitaly. Thank you for inviting me to speak at the seminar, and thank you everyone for being here. So when Vitaly invited me to talk, he actually wanted me to say a little bit more about that part, about the Voronoi conjecture, but I will mostly talk about lattices and the equations that are related to lattices in general. So there are some applied or a little bit more applied things that that are going to discuss, but overall the outline is the following. So I will mostly talk about these four topics. So these are about lattices, packings, coverings, and in general parallelohedras, or what are those and what properties I'm going to discuss, right? So, and the main theme is while I'm working in discrete and computational geometry and in combinatorics, so the main topic will be about polyhedral computation. So it's computationally heavy topics where I think recently it's more and more using of parallel computations with various clusters were very helpful. So the talk is not based only on my results. Actually, the most recent results that I'm going to mention are not mine, but my results are based on several joint works with Mathieu Dutour-Sikirich, Andrei Gavrilyuk, Sasha Magazinov, Achil Shurman, and Clara Val. And feel free to interrupt me if you have any questions or if I can clarify anything. Okay, so let's start. So what are lattices? So lattices are, or full dimensional lattices that I'm to consider. So full dimensional lattice in d-dimensional Euclidean space is a set of all integer linear combinations of a basis. So I choose a basis and I consider all integer combinations of these vectors. So for example, here I have the integer lattice, right? So I can choose two vectors like that and take all linear combinations of integer linear combinations of two vectors. Here I have not really a lattice, because lattice is a set of points. So what I need to do, I need to pick all those vertices of the square tiles, and that will be the integer lattice. But for me, it is much nicer to see some underlying structure for that. So these tiles are helpful as well. And of course, there are many options to do that. Even if I have a point set, then I can choose another basis. So for example, something like that. And then I will get the same collection of points, right? So a way to see that is that if I have two different bases, then the transformation matrix between these bases, it has to be an integer matrix, and the inverse of that matrix will be integer as well. Okay, so another example is another lattice. So this is hexagonal lattice, right? So this is hexagonal lattice. And again, there are many ways to choose a basis. So actually, infinitely many ways. So this is one choice of the basis. So this is another one. So, but these are already from these pictures. You can see that we are dealing with a highly symmetric structures. At least sometimes. Not all lattices are highly symmetric, but some of them are highly symmetric, and some of them look nicer. Look nicer than the others. Okay, so this is the main definition. So what is the motivation for those? The original motivation, or at least as I can see that original motivation, is in crystallographic groups. So lattices are basic examples of crystallographic groups as they appear in so let me hide the video. So as they appear in 19th century study of crystals or of periodic crystals in material science. So mathematically speaking, crystallographic group is a subgroup of isometries of the d-dimensional Euclidean space, or in general of a metric space that has discrete orbits and a compact fundamental domain. So actually in the case of the lattice, so the fundamental domain will be exactly the parallelepiped spanned by vectors of the base. So this is one example of fundamental domain, and I'm being a little bit incorrect here. So it's not really compact because the vertices that I have, or the vertices of the parallelepiped that I have, they belong to one orbit, but I can kind of compactify it, and it will be fairly nice. So for me, it's something that that has these properties. From the point of view of periodic crystals, what we have just one big or relatively big block of a crystal that repeats itself in space, right? And for lattices, I'm just using translations, but in general, as I said, with hexagonal and with the integer lattices, we may have more symmetries. Okay, so from mathematical point of view, lattices appeared in one of the Hilbert's problems. So it's Hilbert's 18th problem, and these questions were motivated by mathematical crystallography. So particularly the first part of the question asked whether it's whether the family of crystallographic groups in d-dimensional space is finite. Second part asked about existence of a polytope that tiles d-dimensional space but cannot be obtained as fundamental region of crystallographic group, right? So if we have a fundamental region, then we can take action of the group and we'll get a tiling, but the question asked whether this holds for any polytope that tiles the dimensional space. And the third question asked about the densest or the most optimal configuration of spheres in three-dimensional space. And this question goes back to Kepler. So this is what it's called, Kepler conjecture. And now, as I'll say in a few slides, it can be called Hale's theorem. So what are the answers to these questions? So for the first part, this was proven shortly after Hilbert formulated the question. So this was proven by Bieberbach in two papers in 1911 and 1912. So he proved that every crystallographic group contains a d-dimensional subgroup of translations, and that's exactly existence of this lattice structure in every orbit of crystallographic group. When we are talking about Euclidean space, there are of course questions for other spaces. For example, for the hyperbolic space, there are also interesting constructions there. And he also proved that there are finitely many options for the quotient, and that gives the finite that gives a finite family of crystallographic groups. So the second part was also answered fairly quickly for mathematics. It took about 30 years for Reinhardt to construct an example in the three-dimensional space, and then Hayes constructed this example in two-dimensional space. So this polygon, it's a non-convex polygon, but it tiles two-dimensional plane, and there is no crystallographic group that has this polygon as fundamental region. And for the third part, so it took 100 years for mathematicians to prove that the densest sphere packing is exactly what everyone knew for 400 years, so or about 400 years. So it was proven by Tom Hales, and the first part was published in 2005, and then 12 years later, it was verified by computer. So he made this very long and detailed effort to make sure that the proof can be verified, because it involved a lot of computations, and some people were complaining that it's too complicated to verify. So the structure that we get, or one of the structures, so here I have the structure that gives the lattice packing. So the underlying red three-dimensional spheres or three-dimensional balls, they are in hexagonal lattice. Then we find some holes and put yellow spheres. Then we find more holes in between the yellow spheres, put blue, and continue to do that in this layered manner. So we may get a lattice packing this way. So that's something that I will talk about shortly as well. So apart from that, apart from the densest packing in the three-dimensional space, the densest packings are known in two-dimensional space, and this is usually treated as folklore. And only in two other dimensions, in 8-dimensional and 24-dimensional space, there are papers by Marina Vezovska and Marina Vezovska with several co-authors, Henry Kohn, Abhinav Kumar, Stephen Miller, and Danila Radchenko. So they proved that the corresponding lattices or the corresponding packings that were known for quite some time before that, they are really the densest packing. So in addition to mathematics, well, mathematical questions about lattices are interesting for me, but I know it's not for everyone. So there are more applications of lattices. So they're used in post-quantum cryptography. So particularly if quantum computers will break RSA, the most standard encryption protocol that we're using right now, there are lattices for us, and they can save us in this post-quantum world. They're also used in error correcting codes to transfer information efficiently. They're used in material science as one of the models of periodic crystals and sometimes aperiodic crystals as well. And they're also give us source for lattice polytopes and all applications for all computer science research that is based on that, including computer graphics and everything else. Right. So this is kind of one of or several directions where lattices could be used, but there are more. Okay. Are there any questions at this moment before I go more into math? Okay, so let me go back or slightly back to the Hilbert questions about lattices. So the first topic that I would like to discuss is about sphere packings. So and particularly about lattice sphere packing. So it's not just any configuration of spheres, but I want to find lattice in d-dimensional space that gives the most efficient packing of spheres when we put them, when we put the centers at points of lambda. So what that means that we want to have spheres centered at the points of the lattice that are not intersecting with each other, but occupy as much space as possible, right? And if we introduce the following two parameters, the determinant of the lattice or the volume of the parallelepiped, so it's a positive number. So maybe the correct way to write it is the absolute value of determinant, right? And lambda 1 is the shortest non-zero vector. Then finding the most efficient packing is the same as maximizing this quantity. So it's d-dimensional. I'm sorry, not d-dimensional. It's lambda 1 raised to the power d, that kind of close to the volume of each sphere, divided by the fundamental volume of the parallelepiped, right? And the idea here is that if I have spheres that are packed, right? So then this shortest distance will be exactly lambda 1, right? And this volume of that parallelepiped will be determined. So when I scale it, this quantity doesn't change. So I really need to find a configuration where determinant is fixed and lambda 1 is as large as possible. Okay, so and this is surprisingly a complicated question. So there are the answers are known only in several small dimensions. So particularly for 2 dimensions, it's known that hexagonal lattice is the best, and this is what is sometimes denoted as the lattice A2. In 3 dimensions, the equation was answered by Gauss. In dimensions 4 and 5, it was answered by Korkin and Zolotaryov, and this was in 19th century. Dimensions 6 through 8 were done by Blichfeld in 1935. The 24-dimensional space, and you can see that again there is this jump from 8 to 24 was done by Kohn and Kumar. And finally, the result that I wanted to mention, so this was done just recently in 2025, posted on arXiv by Mathieu Dutour-Sikirich and Wessel van Verden. So they proved that the 9-dimensional laminated lattice is the best lattice for packing of 9-dimensional spheres. So before I tell a few words about ideas of the proof, so let me introduce the lattices because we will see them a little bit later. So the lattices that are used here and everywhere in my talk are the following. So ZD is just the standard d-dimensional lattice, standard integer lattice. So then there is lattice AD, and this lattice is the collection of all integer points with 0 sum. So it is kind of cross section of the integer lattice. So it has the dimension d. The lattice d with index d is also a subset of the integer lattice, but now we choose all the points where sum of coordinates is even. So actually I need to fix this, right? So this has to be AD, right? So then there are 3 very specialized lattices. So these are called Korkin-Zolotaryov lattices. So these are E6, E7, and E8. It's easier to start from E8, which is just union of D8 with its copy moved to the center of large holes, right? So then there is E7 and E6 are obtained similarly to AD, so we consider slices of E8. In one case, it's orthogonally to a shortest vector, and in another case, orthogonally to a hexagonal sublattice. So a usual question from mathematicians working into questions related to root systems. So how these are related to root systems? So yes, these are related to root systems. So if we have a root system in d-dimensional space and we consider all integer linear combinations, then we will get lattice. So for A system and D system, we get exactly these lattices, right? So in the finally laminated lattices, they are obtained similarly to that construction of the densest packing in three-dimensional space. So we just take the best lattice for packing in d-1 dimensional space and try to place the next layer as efficiently as possible, next layer of spheres as efficiently as possible. So this is this will give us what is called laminated lattice. So if we do that in the 9-dimensional space, we get the 9-dimensional lattice lambda 9. And actually, each lattice, which was lambda 24, can be obtained that way as well if we repeatedly laminate the previous lattices. Okay, so what are ideas of the proof? And actually, the main algorithm, it goes back to works of Voronoi in the beginning of the 20th century. So the main idea here is to consider, instead of considering lattices, we can consider positive definite quadratic forms. And if we start from the set SD of all D minus D symmetric matrices, and we can think of that as a family of matrices with D times D plus 1 over 2 parameters. So it's just all parameters in the upper triangular part of the matrix. So if we consider the cone of positive definite quadratic forms, and these are the matrices that have positive values of for all non-zero vectors x, then we can construct a connection between so we can construct a connection between lattices and positive definite quadratic forms. So we start for a lattice, we can take its Grande matrix, and Grande matrix is a symmetric matrix. As soon as the vectors are linearly independent, we have a positive definite quadratic form. So, and we can also go back. So if we have a positive definite quadratic form, then we can construct a basis with these inner products. So that will give us a lattice. So with this bijection, if we want to find the best lattice for sphere packing, so this is the same as among all positive definite quadratic forms, finding the quadratic form that maximizes the following quantity. And this is already just linear algebra, so there is no geometry here, so it's just linear algebra. So the denominator here is just determinant of the matrix and taken to the power 1 over d, and the numerator is the minimum of this norm defined by Q among all non-zero integer vectors. So we have integer vectors which we plug in inside the quadratic form, and we want to minimize that. So we want to maximize this lambda 1, so maximize the mean. So
Alexey,
how this can, yes.
Could I ask a question here about this gamma, or well, the previous ratio with the power d?
Yes.
Is there an obvious upper bound for this Hermits invariant?
An obvious upper bound, yes. So there is so an obvious upper bound could be that if we have so if we have determinant, so let's suppose determinant is 1, because we don't need anything, right? So we can scale the quadratic form, positive definite quadratic form. So if determinant is 1, then what can we?
Maybe in 2 dimensions. I was wondering, we are simply dividing the area of a disk, right?
Right. So it's, well, we are dividing area. It's not area of a disk, it's area of the parallelogram in that case.
Okay, right. I was sorry.
No,
sorry,
okay.
I was thinking about the squared version.
So, so it's we can think of that as the shortest vector of shortest vector of the lattice, length of the shortest vector divided by the area of the parallelogram. Well, to some extent, right? So it's one so square root of that.
Yep.
And the area of parallelogram is just product of two sides, or if it is a rectangle, so that will give some bound already. I think so, because we need the shortest one, so that gives some upper bound. And
so it's not simply one upper bound. It's more complicated.
It's, well, simple. One is an upper bound because it's a density packing, right? It's a packing density. So one is an upper bound, but that's like very trivial. There should be something a little bit more. I just cannot come up with a trivial explanation why it should be. But in general, yes, so it should be some sphere, since it's packing. It's a packing of spheres, and spheres are round and cannot pack with density 1. That will give some bound. Yeah, but for Hermite constant, it's a little bit different because it's not spheres here, right? So we need to do some computations to come up with it. But there is a not very complicated upper bound here as well. Okay, any more questions? Okay, yes, thank you, Vitaly. So, and how can we find, so what is the algorithm? So actually there is a very nice and not very complicated from algorithmic point of view approach. So it's some more modern version of that approach uses what is called Ryzhkov polyhedron. So if we consider all, so this is SD positive is the set of positive definite quadratic forms. So it's a cone in the space of forms. So if we consider collection of all forms that have minimal value to be at least lambda, so lambda 1 of Q is at least lambda, so then it is called the Ryzhkov polyhedron, and this is really, so this is a polyhedral construction, because what is written here, it says that for every vector for every integer vector except 0, x transpose qx is at least lambda, and this is a linear function, so this is linear in coefficients of q, right? So this is something linear in coefficients of q. So we have a lot of linear inequalities, actually infinitely many linear inequalities, but one can prove that locally there are only finitely many of them involved. So this is a polyhedral construction. And if we consider vertices of that polyhedron, so these are called perfect forms. Actually, this is not a perfect form definition that was introduced by Voronoi, but it can be shown that these are equivalent. And more than 100 years ago, in 1908, Voronoi proved that there are only finitely many non-equivalent perfect forms, and only perfect forms could be optimal for sphere packing. So basically, the algorithm is the following, and this is a very simplified approach, as we will see on the next slide. So we start from a perfect form, then we have a lot of linear inequalities. So from these linear inequalities, we choose only those that are relevant, that will give us edges of the polyhedron at that vertex. So we find all the neighbors. After we found all the neighbors, we identify which of these give us new perfect forms, and here we use, so new here means that we are choosing a basis, so choice of bases in a lattice, right? So we may choose different bases in a lattice. So that's what we are checking here. And there are algorithms to do that. And we repeat this process till no new forms are found. So we have a list of all perfect forms. And from all these perfect forms, we choose the one that is the best for us, that gives the densest packing. So it sounds simple. It can be carried out fairly quickly in small dimensions. And these are the results. So actually, in dimensions up to 5, you don't even need a computer, and maybe up to 6 as well. So it was done by Lagrange, Gauss, and Gauss in dimensions 2 and 3, Korkin and Zolotaryov in dimensions 4 and 5, by Barnes in dimension 6, by Jacquet-Schiffel in dimension 7, by Dutour, Sikkerit, Schurman, and Valentin in dimension 8, and there the number of forms starts to grow. So in the most recent one by Mathieu Dutour, Sikkerit, and Wessel van Verden, so they found more than 2 billion perfect forms in dimension 9. And this was a very extensive computation, polyhedral computation. So for example, we can, so there is a vertex of Ryzhkov polyhedron. Actually, this vertex corresponds to the densest packing, so we cannot avoid it. So that has 5 times 10 to 15 neighbors. And of course, it's impossible just to write them down. Right, so just saving that number of neighbors in a computer will require enormous amount of memory. So what is done there, and that's where Mathieu's magic works. So these computations are done with involving a lot of symmetry. So that lattice is highly symmetric. So I think the order of symmetry is about 10 to the 6 at least. So at the end, you'll get about in the order of billions of neighbors up to symmetry, and that's manageable. I wouldn't say it's easy, but it's manageable. So this is one example of polyhedral computation that is related to lattices. So the second one, and I'm getting closer to the topic Vitaly asked me to cover, right? So I'm getting closer to Parallelohedra. So the second one is a related question, but it's about sphere covering. So this is somehow slightly dual question, not precisely dual, but slightly dual. So what we want to, and this, so one can think of that as a question of placing cellular network towers so that they cover the area as efficient as possible. It's not exactly like that, because we know that there are cities where the population is much denser, so we need more towers there. And in rural areas, we sometimes need fewer towers. But if we are living in a perfect world where we need to cover everything as uniform as possible, so then we kind of may resort to using only lattices. And this is not true in higher dimensions. So in higher dimensions, actually, there are coverings, or there are packings that are non-lattice that are more efficient than all lattice packings that are known. But here we're talking about coverings, and you were using only lattices. So again, we want to find a lattice such that using centers, points of that lattice as centers of the spheres gives us the most efficient cover. So formally, so if we have R, which is the covering radius, so that is the shortest radius of the sphere that allows us to cover everything, then our goal to minimize that value. So, and unlikely, or similarly to the packing, so this is always greater than or equal to 1. So for packing, we have less than or equal to 1 because spheres don't cover everything. See, here we cover everything. Let me write it correctly. So after proper rescale. right? Because this is not the quantity that counts the volume, right? So I need to rescale by the volume of a ball. Okay. So what can we do here? Actually, the best known results are the following. So they are known in dimension up to 5, right? And these are in dimensions 2 and 3, they are due to Kirchner and Bamba. In dimensions 4 and 5 by Delano and Ryzhkov and Baranovsky. And in all these cases, these are lattices AD star, so the dual lattices to the lattice AD. So that's the dual lattice is just the lattice that is generated by dual bases, or the same, we consider all vectors that have integer inner products with the vectors of the original lattice. In dimensions starting from 6, there are no proofs that the known lattices are the best. There are just conjectures, and this was done by Schurman and Valentin. So they, again, used a lot of polyhedral computations to find the best known packing lattices for packing so far. And this is what I will tell a little bit about. So what are these lattices and how we can find? The idea comes from one can say computational geometry. So actually this was done before computational geometry was introduced. So this is what is called Delaunay triangulation. So Delaunay triangulation of given set A is a collection of simplices with vertices in A that uses only empty circumspheres, right? So here in the left, I have a Delaunay triangulation of a general point set, right? And you can see that triangles are have empty simplices, and this is a tool that is used in many applications, starting from pathfinding to computer graphics. So for lattices, we're going to have much more nicer pictures. So here I have a lattice, and if I want to construct Delaunay triangulation, I will just repeat those triangles, and for 2 dimensions, actually, it will give me everything, right? So this will be the Delaunay triangulation of this lattice. So it's much more structured in the lattice case, but in the general case, it has many more applications, right? And of course, if we're thinking about arbitrary lattices or even highly symmetric lattices, so for integer lattice, we don't have triangles where the circumspheres are empty. So then we're going to get a Delaunay tessellation or Delaunay tiling. So, but in our case, I will discuss mostly triangulation. So what is the algorithm? So how we can find the most efficient lattice covering? So actually we go back to positive definite quadratic forms. So if we fix a Delaunay triangulation, so and by fix I mean that we fix integer coefficients of, so we fix a basis and we fix integer coefficients of linear combinations of vectors that are used for simplices of the Delaunay triangulation. So if we fix only these integer vectors, then we have points in the integer lattice, and we can construct what is called the L-type domain. So we take these integer points, we consider only simplices in the integer lattice, and we consider all quadratic forms that give exactly the same simplices, right? So we go from quadratic form to lattice with prescribed basis, then we construct Delaunay triangulation of this lattice. So if the integer vectors are the same, then we are saying that we are in the same L-type domain or in the same L-type. Sometimes it's also called secondary cone, and there is a connection with this secondary cone to secondary polytope for triangulations of for the family of all triangulations of the point set. So this is a connection to that as well, right? So in the same paper, or actually series of 3 papers, Voronoi proved that there are just only finitely many non-equivalent L-type domains or L-types, and there is theorem of Delaunay, Nikolai Dolbilin, who is in the audience. Yes, thank you for that theorem in particular. So Ryzhkov and Stogrin so proved that for every L-type there is exactly one positive definite quadratic form that optimizes the covering density. So basically our goal is to find all L-types, and this can be done by the same polyhedral or similar polyhedral approach. So if we start from an L-type, then there is a local Delaunay property that basically says that if I have 2 adjacent simplices, so then the common phase will give us a linear inequality on the coefficients of the quadratic form. So again, we have infinitely many linear inequalities. We can find just finitely many of those that are relevant. So this is a polyhedral construction. Again, we find all neighbors. So now the neighbors are organized in a slightly different way. So each L type is a polyhedral cone. So the neighbors are across. So these are across facets, not neighbors that are using neighboring edges. Again, identify all new types and repeat till no new types are found. So at the end, we have each L type, and we can find the optimizing form just by picking the best of those optimizing types for our sphere covering problem. And for each L type, this is a convex optimization problem, so this can be done efficiently. So for the classifications, so in dimension up to 4, Voronoi did that classification. So there is 1 type in 2 and 3-dimensional spaces, 3 types in the 4-dimensional spaces. In the 5-dimensional cases, Baranovsky and Ryzhkov found 221 types when they were solving the sphere covering problem. So Engel found 1 that they missed, so there are 222 types. In R6, the situation is much more complicated. So in 2013, Baburin and Engel found roughly 500 million types, and that was not complete classification. So there is more to it than just this. So even in 6-dimensional case, this classification is unknown. So this is about covering. So how now we are finally moving to parallelohedra. So so parallelohedra are related to the covering question in the sense that when we are trying to find all L types, what we are doing, we are trying to find all Voronoi polytopes of lattices. So if we have a lattice, then for this lattice we can construct the polytope that consists of all points that are closer to a fixed point of that lattice than to any other point of the lattice. So this is what is called the Voronoi polytope. And of course, since the lattice is translationally equivalent, when we try to translate that polytope to other vertices of the lattice, we'll get tiling of the space. So or similarly, if we perform that construction for every point, then we get the same polytope or translations of the same polytope. So this is called the Voronoi polytope of the lattice, and it tiles the space with translations on. So the corresponding tiling that we are using here is dual to Delaunay triangulation, or in general to Delaunay tiling. And the reason for that is when we are trying to construct the Voronoi polytope, what we are having, we are drawing perpendicular bisectors between points of the lattice. And when we are constructing Delaunay triangulation, we have empty spheres, and the center of the sphere is constructed using perpendicular bisectors. So these both constructions are related to perpendicular bisectors, and in general, they are geometrically dual to each other. So the blue part here is Delaunay triangulation. The black part is the Voronoi decomposition. So in general, if we forget about that construction and just consider the polytopes that tile the d-dimensional space by translation, so then the corresponding polytope is called parallelohedron. So in other words, so parallelohedra are just polytopes that tile d-dimensional space using translation only. In the two-dimensional space, there are just two types of those parallelohedra. So these are parallelograms, and you can see that we can form brick wall tiling in the left-hand side, so where parallelograms do not share the faces. So in the classical case, when we consider parallelohedra is going back to 19th century, so they are required to share complete faces when they meet each other. So this is what is called face-to-face tiling. And the second one, the central asymmetric hexagon in the right, it is always going to be. So actually, I will consider only that situation, so that the parallelohedra must have face-to-face tiling, and it is known it's a result by Venkov and McMullen, or two independent results by Venkov and McMullen. So if a parallelohedron has any tiling by translation, then it must have a face-to-face tiling. So in the three-dimensional case, there are 5 three-dimensional parallelohedra. They were found by Fedorov in 19th century, and they are he was interested in that due to its connection to crystallography, because these are kind of the fundamental building blocks of three-dimensional crystals. So there are 2 of them that are constructed from the two-dimensional ones are parallelepiped and hexagonal prism with central asymmetric base, and 3 more that are kind of more complicated. So it's if we start from the right, so this is truncated octahedron, elongated dodecahedron, and rhombic dodecahedron. So these are all 5 types of three-dimensional parallelohedron. So this is an example of the tiling with elongated dodecahedra. So it looks complicated. The polytope itself looks complicated, and it's not always easy to imagine that it can tile the space, but even Wikipedia comes to our help to show that this is possible. Okay, so one of the main conjectures in parallelohedra, and it's conjecture from beginning of 20th century, Voronoi conjecture. The conjecture claims that actually our initial construction of Voronoi polytope, or it's sometimes called Dirichlet-Voronoi polytope, is the only construction to get parallelohedron. So every parallelohedron is a finally equivalent to a Voronoi polytope for some lattice, right? And in 2 dimensions, it's fairly easy to prove that. So each parallelogram can be transformed into a rectangle or into a square, and square is a Voronoi polygon for the integer lattice. If we have a central asymmetric hexagon, then we can find a transformation that transforms this hexagon into an inscribed hexagon, and inscribed hexagons are Voronoi polygons. So that's fairly easy in dimension 2. In higher dimensions, it's not that easy. Before I will go into small dimensions, so let me briefly mention some results when the Voronoi conjecture is known. So it is known for primitive parallelohedra, and that means that if we consider parallelohedra where the dual tiling is triangulation, right? So which is the same if we consider parallelohedra where the corresponding tilings have very a small number of or as small as possible number of polytopes that are incident to each vertex. So then it was proven by Voronoi. For d-2 primitive parallelohedra, it was proven by Zhytomyrsky, and that means that if we have tiling, then the d-2 dimensional faces are not that complicated in the tiling. It was also proven by for zonotopes by Erdal at the end of 20th century. So here the connection, there is a connection to oriented metroids. So zonotopes that are parallelohedra actually come from unimodular matrices. So matrices where all minors are zeros or positive or negative ones. So that's a little bit of connection to algebraic combinatorics. For it was also proved by three reducible parallelohedra, and this is extension of case of Zhytomyrsky. So this was proved by Andrei Ordin. And one more result. So let me mention it without explicitly stating what is there, right? But there is a global combinatorial condition for which we can show that if a parallelohedral satisfies this combinatorial condition, then there is a geometric condition that it satisfies, because Voronoi conjecture is about geometry. So here we can say that some combinatorial property of parallelohedra implies geometric property. So this was done by Andrei Gavrilyuk, Sasha Magazinov, and myself about 10 years ago. So this is what I will refer to as GGM condition. So what is done in small dimensions? Actually not much. So in dimension 2, it's kind of folklore, and the proof that I told you works. In dimension 3, it's also kind of folklore. So we know that there are exactly 5 three-dimensional parallelohedra, and one can check that they all satisfy the Voronoi conjecture. Actually, one way to do that is to check the GGM condition that I mentioned before. So all of them satisfy that condition. Then in the 4-dimensional case, it was proven by Delano in 1929. The same paper that gave initial classification of parallelohedra, and the recent paper, last year paper, I'm the only co-author there, but I always say that this paper would be impossible without our collaboration with Sasha Magazinov. Unfortunately, he decided to step down as co-author of the paper, but I think he should be co-author there. I couldn't force him, but I think he should be. So the Voronoi conjecture is true in the 5-dimensional case. So a few words about the proof. So the sketch of the proof is the following. So first of all, we can classify all L types and find all Voronoi primitive parallelohedra. So starting from primitive, then we can find just all parallelohedra, and this was done by Mathieu de Turcy-Kerich, Achille Schurman, and Clara Weidman, and myself in 2016. Then for each of these parallelohedra, we can check that they satisfy the GGM condition, and this was done by Mathieu, Sasha, and myself in 2020. And after that, it's really a careful combinatorial analysis of what could happen. So the ideas there that involve that the ideas that we use there, it's finding local structures at 2-dimensional faces, local structures at edges of these 2-dimensional faces, and actually additional combinatorial properties of parallelohedra that can be stretched. So for example, if we start from let's say a cube, right? So then we can stretch it along any of the edges to get a parallelepiped, and there is a similar property that can be studied for arbitrary parallelohedra, and it gives a lot of combinatorics that can be used to show that every parallelohedron is combinatorially equivalent to one from that list, and then GGM condition is combinatorial property, so then it implies the geometry that we need. So finalizing that topic, so finalizing the classification of parallelohedra, actually we can find all of them in dimension up to 5. So in 2 and 3 dimensions, there are 2 and 5 respectively. In dimension 4, there are 52 parallelohedra, and they were 51 was found by Delaunay, and the last one was found by Stogrin. And in dimension 5, there are 110,244 parallelohedra, and that's result of the, again, computational work, finding all L types and finding parallelohedra from that, and the proof of the Voronoi conjecture from the last. So in the last 3 minutes, so let me tell a short story about 6-dimensional case. So is there any hope to go further? One kind of tool that is used here is what is called C-type domain. So instead of considering all simplices in the Delaunay triangulation, so we can consider just one-dimensional skeletons. And the motivation here is that one-dimensional skeleton tells us a story about shortest vector, because if we have an edge of Delaunay triangulation, then these are two neighboring Voronoi polytope, and this is the shortest vector to some extent, actually shortest vector in a given parity class of the lattice. So, and this is again a linear inequality, which tells us which vector is shortest in each parity class. So again, we can find a polyhedral computation that classifies all C-type domains. So if we start from C-types, then again, we find the corresponding polyhedral cone, we find all neighbors, identify new types, and so on and so forth. So this was recently done in the 6-dimensional case. And again, you can see a combinatorial explosion there, which pretty much tells you that 7-dimensional case is impossible to compute in the same way, right? So there are 55 million different C-types there. So I would say it's a new hope, but there are still difficulties around. So there is one specific C-type of the dual lattice E6 star that has not very many facets, just 216, but 157 million extremal rays. So it's very few facets, but a lot of kind of one-dimensional rays that define. So it has a huge symmetry group, though after talking about symmetry group of laminated lattice lambda 9, it's called probably not huge, but more than usual, 103,000. But if we want to find how many C-types, so how many L-types are there, so then it's a computation that would involve going through approximately 10 to the 19 potential Delaunay triangulations, and that's too much. That's even more than what we had before for the neighbors of lambda 9, right? So nevertheless, it was mathematically, it was possible to find the best sphere covering next to E6 star, and this was done by Achille Schurman and Frank Valentin. Okay, so I think it's about time to stop. So thank you for your attention. So it's not exactly what Vitaly asked me to talk about, but I hope this polyhedral computations is a bit more interesting than theoretical proof of 45 pages about Voronoi conjecture. So thank you.
Okay, thank you, Alexey. Please thank Alexey physically or virtually. I'll stop the recording and